You ever look up at a rocket launch and just think, how the does that even work? Like, seriously, this 300-foot tall skyscraper just casually lights itself on fire, then punches a hole through the sky like gravity doesn't exist. It feels like magic. But it's not. It's the pinnacle of engineering. But how do you go from the drawing board to the edge of space? It starts with one goal: escape Earth. Simple to say, brutally hard to do, because Earth has this annoying little thing called gravity. It's constantly pulling everything down with 9.8 meters per second squared of force. Doesn't sound like much, but to leave Earth, you need to hit escape velocity, which is about 11.2 kilometers per second, or roughly 25,000 miles per hour. Let me say that again. To get to space, you need to launch something as heavy as a building 25,000 miles per hour, straight up. So how do you do that? With fire. Lots and lots of fire. A rocket is basically a metal pipe full of explosives, but designed so precisely that it doesn't blow itself up. We're talking thousands of tons of fuel and oxidizer, mixing them, igniting them, and shooting them out of a nozzle at thousands of meters per second. That reaction is what pushes the rocket upward. This is Newton's third law. For every action, there's an equal and opposite reaction. You push gas down with extreme force, the rocket goes up. But here's the thing. Rockets aren't just big boom tubes. They're surgical instruments wrapped in armor. Everything has to be perfect, because at launch, there are millions of things trying to kill the mission. Let's talk construction. Most rockets are built in stages. Picture it like a Russian nesting doll made of explosives. You've got a big first stage on the bottom that does most of the grunt work, getting you out of the thick atmosphere. Then you've got a second stage that takes over once you're higher up, where the air is thinner and engines can be more efficient. Sometimes there's a third stage too, depending on the mission. But why have these stages? Well, it's all about mass. The more weight you carry, the more fuel you burn. The more fuel you burn, the more weight you need just to lift that fuel. It's a cycle. So instead of carrying the entire structure all the way to space, you dropped empty parts off as you go, shedding weight like peeling off a jacket during a marathon. Now let's get into the fuel. Rockets don't run on gasoline. They use things like liquid hydrogen RP1, which is basically refined kerosene, or hypergolics, which are so reactive that they ignite on contact. Every one of these has its own benefits, but they all need one thing: an oxidizer. Because once you get high enough, there's no air to burn. So you bring your own oxygen, usually liquid oxygen. You've got tanks of fuel and tanks of oxidizer. They get pumped into a combustion chamber, mixed and detonated in a super controlled way. That explosion gets funneled through a rocket nozzle, and boom, thrust. A rocket nozzle isn't just a tube either. It's a precisely shaped bell that converts hot gas pressure into kinetic energy. The narrow part of the nozzle builds pressure. The wide bell expands the gases and directs them outward. That's how you squeeze maximum velocity out of every explosion. Now imagine doing that hundreds of times per second for minutes at a time without missing a beat. That's what rocket engines do. But wait a minute. Every time you've seen pictures of a crew in a rocket when it's taking off, they're all completely strapped in. So how does the rocket know where to go if no one's steering it? And how does it not fly completely out of control? Well, rockets use something called gimbal thrust. That's when the nozzle physically tilts side to side to redirect the flow of exhaust. This lets the rocket steer itself mid-flight. It's like balancing a broom on your hand. You tilt one way to shift the movement. In space, they also use tiny bursts of compressed gas, called RCS thrusters, to rotate and reorient. Now, while all of this is going on, a flight computer is constantly monitoring velocity, acceleration, trajectory, fuel levels, heat, structural loads, engine pressure, you name it. It's like driving a sports car, flying a plane, and juggling knives at the same time, except the whole thing is moving at Mach 10. But since a computer is doing all the work, humans don't have to, which is why they get to sit tight until the rocket's out of the atmosphere. Now that that's out of the way, let's talk about the launch sequence. At T-minus 10 seconds, everything gets real. Supercooled fuel starts flowing. Tanks are pressurized. Valves open. Then
ignition sequence start.
But it doesn't lift off yet. Computers check that everything's stable. Pressure's good. Vibration levels are within range. Only then do the clamps release and the rocket starts to rise.
We have a liftoff. Liftoff on Apollo 11.
It starts very slowly, just barely clearing the tower, but then speed picks up. Fast. About 45 seconds in, you hit maximum dynamic pressure. This is where the rocket is under the most aerodynamic stress. It's punching through thick air at a crazy speed. If anything's gonna break, it'll happen here. Once you survive that, you're in the clear. A few minutes in, the first stage runs out of fuel. That big lower half detaches and either falls back to Earth, or if you're SpaceX, it turns around and tries to land itself. Meanwhile, the second stage ignites and keeps pushing. That second stage keeps firing until you're either in low Earth orbit or on a path to somewhere farther, like the moon, Mars, or deep space. But here's the thing most people don't realize. Getting to space isn't about going straight up. It's about going sideways. To stay in orbit, you need to be moving parallel to the Earth at ridiculous speeds, approximately 17,500 miles per hour. That's how satellites and space stations stay in the air. They're constantly falling around the Earth on a curved path, so they never actually break the outermost layer of the atmosphere. Lose that horizontal speed, and you just fall right back down. That's why most rocket trajectories look curved. They go up and over, building altitude and sideways speed at the same time. Once the rocket's in orbit, the mission changes. Now it's about precision. Satellites get deployed at very specific times, docking maneuvers start, or if it's a crewed mission, the capsule separates and starts preparing for re-entry, or the next leg of the trip. Now that you're up there floating around in space, you'd think the job is done, but that couldn't be further from the truth. Space was never the finish line. It's a minefield of challenges. Let's talk insulation first. Space is unforgiving on both sides of temperature. Extreme heat on one side from the sun, and bone-cracking cold on the other. In orbit, you can go from 250 degrees Fahrenheit in direct sunlight to negative 250 degrees Fahrenheit in the shade. That's brutal. So how do rockets, or more specifically the payloads inside, survive that? Well, they use these things called thermal protection systems, or TPS. These include multi-layer insulation blankets, ceramic tiles, heat-resistant foams, and in some cases, ablative shields, materials designed to burn away during re-entry, carrying heat off with them like sacrificial armor. If it's a reusable capsule, like SpaceX's Dragon or NASA's Orion, you're relying on these shields to keep the crew alive during re-entry. The capsule hits the atmosphere at over 17,000 miles per hour, and the friction can heat the surface up to 3,000 degrees Fahrenheit. So if your TPS fails, you're toast. Literally. Now let's talk orbit mechanics, because getting into deep space is hard, but staying there or transferring to another orbit, that's a whole different ballgame. Let's say your rocket puts a satellite into low Earth orbit, around 300 to 500 kilometers up. Cool, but what if your mission is to go higher? You can't just go straight there. You have to use orbital maneuvers like Hohmann transfers. Basically, you fire your engines at the right time to shift your orbit in a smooth, energy-efficient way. These are timed to perfection. One wrong burn and your satellite misses its destination by hundreds of miles. And once you're up there, you don't just sit still. Earth's gravity, moon's gravity, solar radiation pressure, all of these things and more can slowly pull your craft off course. That's why satellites carry tiny thrusters to make course corrections. That's also why old satellites eventually drift and turn into space junk. Let's not forget about the launch site though. You can't just launch a rocket from your backyard. Launching into orbit doesn't just require power, you need precision. Earth rotates from west to east, so launching eastward gives your rocket an extra velocity boost from Earth's spin. That's why places like Kennedy Space Center in Florida are perfect. They're near the equator, where Earth's surface spins the fastest, giving rockets a helpful push. You also want to launch over the ocean whenever possible, because if things go wrong, which they usually do, debris lands in the water, not in a city. Now let's talk safety systems, because when you're sitting on a controlled explosion, you need a backup plan. Modern crewed rockets have launch escape systems, basically a mini rocket on top of the capsule that can fire and pull the crew away from the main booster in case something goes wrong. This isn't science fiction, it's been used before, and it works. During a 2018 Soyuz launch failure, the crew capsule detached mid-flight, coasted back to Earth, and landed safely. Total badass move by engineering. On board, you've got redundant computers, duplicate wiring paths, pressure sensors, accelerometers, gyros, and way more, all working together to monitor every part of the system. If anything looks sketchy, the computer can shut it down before disaster hits. Everything I've covered so far leaves us with one last thing: money. Because if you're putting a rocket into space, you're gonna need a whole lot of it. A single launch can range from $60 million, like the SpaceX Falcon 9, to $2 billion, like NASA's SLS. That's why companies are pushing for reusability. Rockets like Falcon 9 can land themselves and fly again, saving hundreds of millions of dollars. That's not just cool, that's the future. When rockets are reusable, space becomes way more accessible. You get lower costs, faster turnaround, and Katy Perry in space for some reason. In reality though, I'm just a dude who likes science. So if you want to learn more about cool stuff like this, hit the subscribe button. Like, just do it. It's not rocket science. I don't know what you're waiting for.